Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module General Treatment of Angular Momentum from paper Quantum Mechanics. So students, let us see what we are going to learn in this module. In this module, we will learn to identify angular momentum as a generator of infinitesimal rotations in three-dimensional space. We will know that the origin of commutation relations lies in the geometric properties of rotations and the need to generalize the definition of angular momentum. We will come to know the significance of ladder operators, or what are also called raising and lowering operators. We will derive the matrix representation for the components of operator Jx, Jy, Jz and operator J square, that is angular momentum J. We will know the representations of the eigenstates as column vectors on which the angular momentum operators for each value of J can operate. We will know the Pauli spin matrices and the important properties. The present module is in continuation of the preceding one. Here, we analyze the connection of orbital angular momentum with rotation in space. Starting from the commutation relations of the angular momentum operators, we deduce the expressions for the eigenvalues of the diagonal operators in the common basis represented by the state where J and M labeling respectively the eigenvalues of operator J square and that of operator Jz. We shall then obtain the matrix representation for the components of the angular momentum operator J. Considering a few specific values of the angular momentum such as J is equal to 0, half, 1 and J is equal to 3 by 2, we shall write their matrix representations explicitly. It is remarkable to note that the eigenvalue spectrum includes not only the integral but also the half integral values of J. As we already know, half integral values of J describe the intrinsic spin of the particles such as an electron or a proton. We describe the spin matrices for the spin half particles first introduced by Pauli and briefly mention their important properties. Now we discuss the angular momentum as the generator of infinitesimal rotations. To get physical insight into the nature of the orbital angular momentum, let us analyze its connection with rotations in space. Consider the case of a change of representation induced by a rotation of coordinate system, that is from frame S OXYZ to frame S prime OX prime Y prime Z prime, which is obtained by rotating the axis through an angle theta about OZ. As a result, a point whose coordinates in S are described by position vector r, a function of xyz, will have coordinates described by position vector r prime, which is a function of x prime y prime z prime in S prime and is given by x prime is equal to x cos theta plus y sin theta. Y prime is equal to minus x sin theta plus y cos theta and z prime is equal to z. The wave function psi prime describing the rotated state must be equal to the original wave function psi at the point. That is because of rotational invariance. We begin with the understanding of angular momentum as the generator of infinitesimal rotations. To get physical insight into the nature of the orbital angular momentum, let us analyze its connection with rotations in space. Consider the case of a change of representation induced by a rotation of coordinate system from S OXYZ to S prime O x prime y prime z obtained by rotating the axis through an angle theta about OZ. As a result, a point whose coordinates in S are given by position vector r of xyz will have coordinates r prime of x prime, y prime, z prime in S prime, where the x prime is given by x cos theta plus y sin theta, y prime is equal to minus x sin theta plus y cos theta, and z prime is equal to z. The wave function psi describing the rotated state should be equal to the original wave function psi at the point. That is, because of rotational invariance, we have psi prime of vector r prime is equal to psi of vector r. On substituting for vector r prime from equation 1 and assuming to be infinitesimally small, we write psi prime of x plus y theta, y minus x theta, z is equal to psi of x, y, z. It is, however, more convenient if we replace x plus y theta by x and y minus x theta by y on both sides of the equation. We thus have psi prime of x, y, z is equal to psi of x minus y theta, y plus x theta, z. Using the Taylor series expansion for psi on the right hand side and retaining only the first term in the expansion, we get psi prime of xyz is equal to psi of xyz plus theta into within the brackets minus y into del by del x plus x into del by del y brackets close of psi of xyz. We note that the differential operator appearing in equation 4 can just be identified as the z component of the angular momentum operator Lz. That is, operator Lz is equal to minus iota h cut into within the brackets x into del by del y minus y into del by del x. It thus enables us to write psi prime of xyz is equal to within the brackets 1 plus iota theta operator Lz divided by h cut bracket close acting on psi of xyz. It is therefore said that operator Lz by h cut plays the role of the generator of infinitesimal rotations. In general, if the rotation is about an arbitrary axis along the unit vector n, then equation 6 can be written as psi prime of r is equal to within the brackets 1 plus iota theta of unit vector n dot vector L divided by h cut brackets close acting on psi of r. For a rotation through a finite angle theta, we sum up the series instead of retaining only the first term, and we get psi prime of r is equal to exponential of iota into theta into unit vector n dot L divided by h cut into psi of r. The important point to note from this study is that the origin of the commutation relations lies in the geometric properties of rotations in three-dimensional space, and that these relations are very general, including those of operator Lx, operator Ly, and operator Lz as a special case. We therefore adopt a more general point of view and define an angular momentum operator J with three components, operator Jx, operator Jy, and operator Jz, satisfying the commutation relations given as the commutator of operator Jx with operator Jy is equal to iota h cut operator Jz. Commutator of operator Jy, operator Jz is equal to iota times h cut operator Jx. The commutator of operator Jz with the operator Jx is equal to iota times h cut operator Jy. We also introduce the operator J square is equal to operator Jx square plus operator Jy square plus operator Jz square. It is a simple exercise to show that operator J square commutes with each of the components operator Jx, operator Jy and operator Jz. That is, the commutator of operator J square with operator Jx is equal to commutator of operator J square with operator Jy is equal to commutator of operator J square with operator Jz and is equal to 0. Next, we discuss the simultaneous eigenstates of operator J squares and operator Jz. We shall now show that the commutation relations described by equation 9 determine the quantum properties of the angular momentum. That is, the eigenvalues and eigenvectors of the angular momentum operator are determined completely by equation 9 and the general properties of the Hilbert space. Since the components of the angular momentum do not commute among themselves, one cannot find a common basis for all three components. However, because operator J square commutes with operator J, we can have a common basis for operator J square and any one component, say operator Jz of operator J. Also note that the eigenvalues of operator J square and operator Jz are real since they are Hermitian operators. It is therefore possible to find a complete set of simultaneous eigenstates of operator J square and where any one component of operator J which we choose to be operator Jz. Let us represent such a common basis by the state ket Jm, where J labels the eigenvalues of operator J square and M represents those of operator Jz. The state vectors given by ket Jm are orthonormal. That is, the scalar product of J prime M prime with Jm is equal to delta J J prime delta M M prime. By definition, operator J square acting on ket Jm is equal to h cut square lambda j acting on ket Jm. Similarly, operator Jz acting on ket Jm is equal to h cut into m into ket Jm. Note that operator J square being the sum of the square of Hermitian operators is definitely positive. Therefore, lambda j, which is given by the scalar product of Jm with operator J square ket Jm divided by h cut square is greater than equal to 0. It is also clear that the scalar product of Jm with operator J square acting on ket Jm is equal to the expectation value of operator J square, which is equal to expectation value of operator Jx square plus the expectation value of operator Jy square plus the expectation value of operator Jz square and is greater than equal to operator Jz square. That is, lambda j h cut square is equal to operator Jx expectation value of operator Jx square plus expectation value of operator Jy square plus m square h cut square. Since Jx and Jy are Hermitian, so operator Jx square and operator Jy square are positive operators and therefore their expectation values are necessarily positive. It follows that lambda j is greater than equal to m square and is greater than equal to 0. At this stage, it is convenient to introduce the ladder operators given by operator j plus is equal to operator jx plus iota times operator jy and operator j minus is equal to operator jx minus iota times operator jy. The commutation relations described by equation 9 can readily be expressed in terms of operator j plus, operator j minus and operator jz as the commutator of operator jz with operator j plus is equal to h cut times operator j plus. Similarly, the commutator of operator jz with operator j minus is equal to minus h cut operator j minus. We note that operator j plus and operator j minus are not Hermitian operators. Instead, the conjugate of operator j plus, complex conjugate of operator j plus is equal to operator j minus, and complex conjugate of operator j minus is equal to operator j plus. The square of the angular momentum operator can be expressed in the following forms. Operator j square is equal to operator jx square plus operator jy square plus operator jz square. This is equal to operator j minus into operator j plus h cut times operator jz plus operator jz square, which can be simplified to have operator j plus operator j minus minus h cut operator jz plus operator jz square. This can be easily seen if we remember that operator j minus operator j plus is equal to operator jx minus iota operator jy multiplied by operator jx plus iota times operator jy. This is equal to operator jx square plus operator jy square plus iota times operator jx operator jy minus iota operator jy operator jy, which is equal to operator jx square plus operator jy square minus h cut operator jz. Similarly, one can find that operator j plus into operator j minus is equal to operator jx square plus operator jy square plus h cut operator jz. Using these relations, it is simple to express equation 20a in the forms given in equation 20b and 20c. Since the ladder operator j plus and j minus commute with operator j square and operator j plus minus ket jm are eigenvalues of operator j square having the same eigenvalue as that of ket jm, that is, operator j square acting on operator j plus minus ket jm is equal to h cut square lambda j operator j plus minus acting on ket jm. But note that operator jz operating on ladder operator j plus minus ket jm can be worked out using the commutation relations described by equation 18a and 18b to give operator jz acting on operator j plus minus ket jm is equal to operator j plus minus operator jz plus minus h cut times operator j plus minus acting on ket jm, which can be simplified to have n plus minus 1 h cut operator j plus minus acting on ket jm. This shows operator j plus ket jm is an eigenvector of operator jz belonging to the eigenvalue m plus 1, whereas operator j minus acting on ket jm is an eigenvector of operator jz with the eigenvalue m minus 1. On comparing with equation 13a and 13b, we conclude that operator j plus acting on ket jm gives a state ket j m plus 1 apart from a possible normalization constant, while operator j minus ket jm is proportional to ket j m minus 1. So we can thus write operator j plus ket jm is equal to Cjm plus h cut ket jm plus 1, and operator j minus ket jm is equal to Cjm minus h cut ket jm minus 1. We thus write operator j plus acting on basis ket described by jm is equal to h cut into cjm plus ket jm plus 1, and operator j minus acting on basis ket described by jm is equal to h cut into cjm minus ket jm minus 1, where cjm plus and cjm minus are the normalization constants to be determined. From equations 25 and 26, it is important to notice that while the effect of the operator j plus on the state jm is to increase the eigenvalue of jz by 1 unit, that is, it raises the state to ket jm plus 1. The operator j minus acting on the state described by ket jm lowers the state to ket jm minus 1, resulting in reducing the eigenvalue of operator jz by 1 unit. It is for this reason that the operators j plus and operators j minus are respectively known as raising and lowering operators, or they may also be termed as ladder operators. The repeated operation of the operator j plus on equation 25 shows that the given state described by ket jm would go on increasing the index m to m plus 1, to m plus 1, m plus 2, m plus 3, and so on. Similarly, the operator j minus would be lowering it to m minus 1, m minus 2, m minus 3, and so on. But clearly, the series must terminate. Otherwise, we would have vectors like described by the basis ket jm prime, which violate the inequality given in equation 16. Since lambda j is not changed by the application of operator j plus minus on basis ket described by jm. This means in order to terminate the series, there must exist a maximum value, say mz, for which operator jz acting on ket jmz is equal to 0. Operator jz acting on ket described by jm2 is equal to 0. Similarly, there must be a minimum value, say m1, for which the lowering operator j minus acting on basis ket described by jm1 is equal to 0. Since the states described by jm1 and jm2 are obtained from basis ket described by jm by repeated applications of operator j plus and operator j minus respectively, we must have a condition that m2 minus m1 is equal to a positive integer or 0. Now, the state vector, which is operator j plus acting on ket basis ket described by jm2 is equal to 0. This implies that its norm is 0. That is, operator j plus acting on basis ket described by jm2 dagger complex conjugate of operator j plus acting on basis ket described by jm2 into operator j plus acting on basis ket described by jm2 is equal to 0. Or I can say the eigenvalue of operator j minus operator j plus is equal to 0. That is, complex conjugate of operator j plus acting on ket jm2 into operator j plus acting on ket jm2 is equal to 0. Or I can say scalar product of jm2 with operator j minus operator j plus acting on ket jm2 is equal to 0. Using the equation 21, that is, operator j minus operator j plus is equal to operator jx square plus operator jy square minus h cut operator jz is equal to operator j square minus operator jz into operator jz plus h cut in equation 27, and using equations 13a and 13b, we get lambda j is equal to m2 into m2 plus 1. Similarly, the equation operator j minus acting on ket jm1 equals 0 gives lambda j is equal to m1 into m1 minus 1. Now equating equations 29 and 30, we have m2 into m2 plus 1 is equal to m1 into m1 minus 1, or I can say m2 plus m1 into m2 minus m1 plus 1 equals 0. This shows that either m2 minus m1 is equal to minus 1 or m2 is equal to minus m1. Out of the two, first one is ruled out because of the condition described by equation 27, and therefore only the second, according to which the minimum value is the negative of the maximum, is an acceptable solution. Now lambda j being the eigenvalue of operator j square depends only on j. So that from equations 29 and 30, one concludes that m2 and m1 should be functions only of j. The choice m2 is equal to j and m1 is equal to minus m2 is equal to minus j, leading to the requirement that m2 minus m1 is equal to 2 times j is equal to a positive integer or 0 meets these conditions. As m2 minus m1 can be 0 or a positive integer, so j can have the values ranging from 0, 1 by 2, 1, 3 by 2, 2, 5 by 2 and so on till infinity. According to equation 29, the eigenvalue lambda j is given by lambda j is equal to j into j plus 1, and m can take the values in the range minus j to plus j differing by integer. Since m can change by integer only, that is m can take the values minus j plus 1, minus j plus 2 and so on till plus j minus 1 and plus j. We have thus obtained the eigenvalue spectrum of the angular momentum operator j, just starting from the commutation relations between the components of angular momentum and the basic postulates of quantum mechanics. The remarkable point to note is that half integral values of j have emerged from this general treatment in a natural way. As we know, half integral values of j are possible only when spin is involved. For a given value of j, there are 2j plus 1 linearly independent state vectors corresponding to 2j plus 1 different values of m given by equation 32b. They are the common eigenvectors of operator j square and operator jz. The state vectors described by ket jm for m is equal to minus j to plus j constitute the complete orthonormal base. Let us now discuss the matrix representation of the angular momentum operator j in the ket jm basis. The state vectors described by jm basis for m is equal to minus j to plus j constitute the complete orthonormal basis for a 2j plus 1 dimensional subspaces, providing the angular momentum representation in which any function of the angular momentum components will be represented by a matrix having elements described by the scalar product of j prime m prime with operator a acting on ket jm. The rows of the matrix will be labeled by various values of j prime and m prime and the columns by j and m. As we have learned, the basis states are the eigenstates of the matrices of these operators must be diagonal. In fact, just using the equations 13a and 33, we can write the scalar product of j prime m prime with operator j square ket jm is equal to j into j plus 1 into h cut square delta j j prime delta m m prime, or I can say the scalar product of j prime m prime with operator jz acting on ket jm is equal to m times h cut delta j prime into delta m prime. The inner product of j prime m prime with operator j square ket jm is equal to j into j plus 1 h cut square delta j prime delta m prime. The scalar product of j prime m prime with operator jz ket jm is equal to m into h cut delta j prime delta m prime. As far as the operators j plus and j minus are concerned, taking the scalar product of ket j prime m prime with equations 25 and 26, we write the matrix elements as the scalar product of j prime m prime with operator j plus ket jm is equal to cjm plus h cut delta j prime delta m prime m plus 1. Similarly, the inner product of j prime m prime with operator j minus ket jm is equal to cjm minus h cut delta j prime delta m prime m minus 1. The values of the constants cjm plus and cjm minus can be determined by equating the norms of the two sides in each of equations 25 and 26. Thus, from equation 25, we get operator j plus ket jm is equal to cjm plus h cut ket jm plus 1. Note that the bra conjugate to operator j plus ket jm is bra jm operator j minus, since the complex conjugate of operator j plus is equal to operator j minus. So, the left hand side of equation 35a can be evaluated by using equation 21, that is scalar product of jm with operator j minus operator j plus ket jm is equal to the scalar product of jm with operator j minus operator jz square minus h cut operator jz acting on ket jm is equal to, within the brackets, j into j plus 1 minus m square bracket close h cut square. We now equate the right hand sides of equation 35a and 36 to get cjm plus is equal to square root of j minus m into j plus m plus 1. In the same way, we can evaluate cjm minus using equation 35b. Here, since from equation 22, operator j plus operator j minus acting on ket jm is equal to operator j square minus operator jz square plus h cut operator jz ket jm, we shall find that cjm minus is equal to square root of j plus m into j minus m plus 1. The matrix elements of operator j plus and operator j minus are thus determined completely. Using the relations described by equation 17, one can then express operator jx is equal to 1 by 2 of operator j plus operator j minus, and operator jy is equal to minus iota by 2 operator j plus minus operator j minus. Let us now recapitulate the important results that we have arrived at. The scalar product of j prime m prime with operator j square ket jm is equal to j into j plus 1 h cut square delta j prime delta m prime. The scalar product of j prime m prime with operator jz ket jm is equal to m into h cut delta j prime delta m prime. The scalar product of j prime m prime with operator j plus ket jm is equal to, within the brackets, square root of j minus m into j plus m plus 1 bracket close h cut delta j prime delta m prime m plus 1. The scalar product of j prime m prime with operator j minus ket jm is equal to j plus m into j minus m plus 1 is equal to square root of j plus m into j minus m plus 1 into h cut delta j prime delta m prime m minus 1. From the above equations, the matrix elements for jx and jy can be written as the scalar product of j prime m prime with jx ket jm is equal to 1 by 2 h cut delta j prime into within the curly brackets square root of j minus m into j plus m plus 1 into delta m prime m plus 1 plus square root of j plus m j minus m plus 1 into delta m prime m minus 1 curly brackets close. The next matrix element given by j prime m prime operator jy ket jm is equal to 1 by 2 iota h cut delta j prime into within the brackets curly brackets square root of j minus m into j plus m plus 1 into delta m prime m plus 1 minus square root of j plus m into j minus m plus 1 into delta m prime m minus 1 curly brackets close. From the above results, it is clear that the matrices representing the angular momentum operators, that is jx, jy, jz, raising and lowering operators j plus, j minus and operator j square are all diagonal in j in the basis jm. Thus, for a given value of j, that is j is equal to 0, half, 1, 3 by 2, 2 and so on, we have an infinite number of representations for these matrices having 2j plus 1 columns and rows labeled respectively by the values of m and m prime. One can either consider all these representations together to form a single representation of infinite rank or consider each of these representations of 2j plus 1 dimension separately. Here, for illustration, we just write the first 4 finite dimensional representations for j is equal to 0, 1 by 2, 1, 3 by 2 for the operators jx, jy, jz and operator j square. In writing the explicit matrices, the convention is followed of placing the element for m prime is equal to j in the first row, m prime is equal to j minus 1 in the second row, etc. and m is equal to j in the first column, m is equal to j minus 1 in the second column and so on. For the case j is equal to 0 for which m is equal to 0, we have simply operator jx is equal to 0 matrix. Similarly, operator jy is equal to 0 matrix, operator jz is equal to 0 matrix, operator j square is equal to 0 matrix, where 0 represents the null matrix of unit rank. For j is equal to 1 by 2, we have operator jx for m prime is equal to 1 by 2, m is equal to 1 by 2 is equal to 0, which is equal to operator jx for when m prime is equal to minus 1 by 2 and m is equal to minus 1 by 2. Operator jx for m prime is equal to 1 by 2 and m is equal to minus 1 by 2 is equal to 1 and is equal to operator jx for m prime is equal to minus 1 by 2 and m is equal to plus 1 by 2. Similarly, the elements for the operators can also be written. The matrix representation of operator jx in the basis spanned by the eigenket half m is equal to h cut by 2, the matrix with the first row 0, 1 and the second row as 1 and 0. Similarly, the matrix representation of operator jy in the basis spanned by the eigenket half m is equal to h cut by 2 into matrix in the first row 0 minus iota and the second row being iota and 0. The matrix representation of operator jz in the basis spanned by eigenket half m is equal to h cut by 2 into a 2 cross 2 matrix with first row being 1 and 0 and second row being 0 and minus 1. The matrix representation of operator j square in the basis spanned by eigenket half m is equal to 3h cut square by 4 into a 2 cross 2 matrix with the first row being 1, 0 and second row as 0 and 1. For j is equal to 1, we have the possible values of m and m prime equals plus 1, 0 and minus 1. As a result, we have 3 cross 3 matrices. Matrix representation of operator Jx in the basis spanned by the eigenket Lm is equal to h cut by square root of 2 into a 3 cross 3 matrix with first row being 0, 1, 0, second row being 1, 0, 1 and third row being 0, 1, 0. The matrix representation of operator Jy in the basis spanned by the eigenket Lm is equal to h cut by 2 into a 3 cross 3 matrix with first row being 0 minus iota 0, second row being iota 0 minus iota and third row being 0 iota 0. The matrix representation of operator Jz in the basis spanned by the eigenket Lm is equal to h cut into a 3 cross 3 matrix with first row being 1, 0, 0, second row being 0, 0, 0 and third row being 0, 0 minus 1. The matrix representation of operator j square in the basis spanned by the eigenket Lm is equal to 2h cut square into a 3 cross 3 identity matrix. Similarly, for j is equal to 3 by 2, we have the possible values of m and m prime equals plus 3 by 2, plus 1 by 2, minus 1 by 2 and minus 3 by 2. As a result, we have 4 cross 4 matrices which are given in the text module. As to the question regarding the state vectors on which the above matrix representations of the components of angular momentum j are to operate, we know that the representation of an arbitrary state defined by ket psi with respect to the basis ket jm would be a column vector whose elements are given by the scalar product of jm and psi. The dimensionality of the column vector would depend on the values that m can take for a given j. For example, for j is equal to 1 by 2, m can take two values, that is plus half and minus half, and it has two elements which are labeled by m is equal to plus 1 by 2 and m is equal to minus 1 by 2. The eigenvectors are thus given by ket alpha is equal to ket j is equal to the basis vector defined by j is equal to half and m is equal to plus half, and ket beta is equal to the basis vector defined by j is equal to half and m is equal to minus half. In matrix notation, the eigenvectors are given by alpha is equal to a column vector with alpha 1 and alpha 2 as elements, and beta is equal to a 2 cross 1 column vector with beta 1 and beta 2 as elements. Since these constitute an orthonormal set and are also the eigenvectors of the operator, the simplest representation satisfying these conditions would be alpha is equal to a 2 cross 1 matrix with first element being 1 and the other being 0, and beta is equal to another 2 cross 1 matrix with first element being 0 and second being 1. In a similar way, for j is equal to 1, m can take the values plus 1, 0 and minus 1. Thus, we would have three independent elements. The eigenvectors are given by eigenvector alpha is equal to the basis vector defined by j is equal to 1 and m is equal to 1. Eigenvector beta is equal to the basis vector defined by j is equal to 1 and m is equal to 0. Eigenvector gamma is equal to The base is defined by j is equal to 1, m is equal to minus 1. There will be in general 3 column vectors with each of 3 elements. The simplest representation constituting an orthonormal set of eigenvectors are alpha is equal to a 3 cross 1 column vector with the first element being 1 and rest all being 0. Beta is equal to a matrix 3 cross 1 matrix with the second element being 1, rest all being 0, and gamma is equal to a 3 cross 1 matrix with the last element being 1 and rest being 0. Similarly, for a particle or a system with j is equal to 3 by 2, we have the possible values of m equals 3 by 2, 1 by 2, minus 1 by 2 and minus 3 by 2. Thus, we have a representation of an orthonormal set of eigenvectors. We next introduce you to the Pauli spin matrices. You all know that electrons, neutrons and protons, which are the building blocks of atomic and nuclear physics, have intrinsic spin half. The non-relativistic theory of spin half particles was first developed by W. Pauli in 1927. Denoting the spin vector by S, which is written as S is equal to h cut by 2 vector sigma, where the vector sigma has the components sigma x, sigma y, sigma z, which are called the Pauli spin matrices and are defined as sigma x is equal to a 2 cross 1 matrix with first row being 0, 1 and second row being 1 and 0. Sigma y is equal to another 2 cross 2 matrix with first row being 0 minus iota and second row being iota 0. Sigma z is equal to a 2 cross 2 matrix with first element being 1 0 and second with the first row being 1 0 and second row being 0 and minus 1. On comparing these matrices, those given for j is equal to half, following properties of Pauli spin matrices can be verified. The commutator of sigma I and sigma j is equal to 2 times iota epsilon ijk sigma k. The anti-commutator of sigma I sigma j is equal to 2 times delta ij. The product of sigma I and sigma j is equal to delta ij plus iota times epsilon ijk sigma k. The trace of sigma k is equal to 0 and determinant of Pauli spin matrices represented by sigma k is equal to minus 1. Note that while writing the above relations, we have replaced the xyz components by 1, 2, 3 respectively, which are denoted by indices I, j or k, each taking the values 1, 2, 3. The two basic spin is equal to half eigenstates alpha and beta given by equation 43 correspond to the spin up and spin down states respectively. They satisfy the orthonormality relations. The scalar product of alpha with itself is equal to the scalar product of beta with itself and is equal to 1. The scalar product of alpha with beta is equal to the scalar product of beta with alpha and is equal to 0. Operator S square acting on alpha is equal to 3 by 4 h cut square alpha. Operator S square acting on beta is equal to 3 by 4 h cut square beta. Operator Sz acting on alpha is equal to h cut by 2 alpha. Operator Sc acting on beta is equal to minus h cut by 2 beta. Introducing the raising and lowering operators where S plus minus is equal to operator Sx plus minus iota times operator Sy, and using the general relations for j is equal to 1 by 2 and m is equal to plus minus 1 by 2, we write operator S plus alpha is equal to 0. Operator S plus acting on beta is equal to alpha. Operator S minus acting on alpha is equal to beta and operator S minus acting on beta is equal to 0. From these relations, we can now write the operation of the x and y components on alpha and beta states as operator Sx acting on alpha is equal to h cut by 2 times beta. Operator Sx acting on beta is equal to operator h cut by 2 times alpha. Operator Sy acting on alpha is equal to I h cut beta by 2. Operator Sy acting on beta is equal to minus iota h cut by 2 alpha. Operator Sc acting on alpha is equal to h cut by 2 alpha. Operator Sc acting on beta is equal to minus h cut by 2 beta. So students, let us now summarize what we have learned in this module. In this module, we have studied to identify angular momentum as a generator of infinitesimal rotations in 3D space. We have come to know that the origin of commutation relations lies in the geometrical properties of rotations and the need to generalize the definition of angular momentum. We have come to know the significance of ladder operators, or what are also called raising and lowering operators. We have derived the matrix representations for the components operator Jx, operator Jy, operator Jz and operator J square of angular momentum operator J. We know the representations of the eigenstates as column vectors on which the angular momentum operators for each value of J can operate. Also, we have come to know the Pauli spin matrices and their important properties. Thank you students for your attention.